Hey, this is George Bunjet with Engineering for All. For a while, discussing with the students, I wanted to make this video that shows an alternative to Newton's second law when we are modeling systems that are complicated for control or vibration classes or other types of projects. Here is a typical problem for vibrations and also for control if we want to use it. The way I'm presenting is what I am trying to present is an alternative to Newton's second law. And this is based on mechanical impedances, which is an analogy made with the electrical impedances from Kirchhoff's laws, which are based on the energy conservation law. So here is, for example, a typical problem that we have at 2 degrees of freedom for a car suspension, and modeling the suspension of a car. We can see that we have the mass of the car, and we have the shock absorbers, that what we call it, these systems, and where they are composed, as we know, from a spring and a damper. And then, so, this can be modeled in 1 degree of freedom, 2 degrees of freedom, 4 degrees of freedom, and so on. So for our case, we start with the 2 degrees of freedom. The 1 degree of freedom is simple. You can solve it easily with Newton's second law. But this one, it becomes a little bit tedious if you use Newton's second law for this. So we'll look at an alternative that we said that is going to help us to just, by observation, look at the system and write the differential equations that are modeling the system. So let's just do it. We can see that the mass of the car can be lumped. In this case, let's assume that we lump the whole mass of the car, the body of the car and the passengers. And then we have the suspension, where we have the spring and the damper. And then we are modeling the tire assembly as a mass. Of course, we have a stiffness in the tire and a damper also, damping properties of the tire. And this is, because we are having the car is riding on the road. If the road is wavy, it will make the suspension vibrate. And we want to somehow make a model and a project in such a way that we are removing or canceling these in vibrations that come from the road. So there is no external force applied to the mass in here, other than, of course, the car is traveling. But that doesn't affect if the road is straight, and that will not affect the suspension if the car is moving. Only when the road is wavy and it has bumps and holes in it, that's going to happen, the vibration in the suspension. So how do we model this 2 degrees of freedom? Well, this is the alternative I am presenting here. And we know that we have in this most of the mechanical systems are defined by these three properties, and where we have constitutive relationships here. We have a stiffness for a spring, we have a damper that opposes the speed of that motion of the mass, and we also have an inertia term. So these are in time domain, the constitutive relationships, where the x dot represents velocity and x double dot represents acceleration. So here it's also, as we most of the time would like to work in Laplace domain, and assuming that we have zero initial conditions. Of course, I will check on we have non-zero initial conditions, another video I'll make it. So here is for zero initial conditions, we have the impedance, which is again analogies with the electrical impedances. For the spring, impedance for the damper, and impedance for the inertia. And that's because, as you can see, we have an S term here because we have a derivative of the displacement for the damper, and we have a second derivative for the acceleration. This is the second derivative of the displacement. So how do we use this in what we call it the algorithm of mechanical impedances? So we can write equations like we see here. Being a 2 degrees of freedom system, we end up with two differential equations. So that in Laplace domain, they will be algebraic equations. So this is the situation for, as we can see here, for the this displacement or state xc of the car, and we have the second state xt of the tire, and we also have another state which is an input for us, because this is the displacement of the road will move the tire up and down, and it will introduce vibrations in the car. So in that case, you can see that when we write this, and you can check these equations with Newton's second law. So when we write this, we have all the, we sum all the impedances that are connected to this state xc, and we have to subtract whatever energy is lost through the connections toward the mass, the second mass. You know, there is a connection between xc and xt, you know, the tire, the displacement of the tire through this spring and the damper. And then we have to equal that with all the forces, external forces that are applied to mass c, you know, at xc basically. And then we do the same thing for the second mass, for the tire. We have a sum of forces, in this case, everything that we have inertia with term, we have two damping terms, and we have two stiffness terms. They all get in here, added together. And then we have to subtract whatever terms our energy may exist. We can say they are transferred to the road, I mean, connected with that, and also energy connected here, there's lost or received, in other words. So that should be transferred. Subtracting. So, and then everything is equal with all the forces that are applied to this mass mt, that xt. So this is the whole algorithm. And as we practice it, you can see how easy it is to write the equations. Say, right now I'm zooming it a little bit, and then I'm gonna start to write the equation for xc in here. So I will have an inertia term, which is the mass mc times s squared. This is the inertia. Then I will have to add the damping term, which is the c s from the suspension times the s term from the derivative. And then I have the stiffness term, k there. Everything in here is multiplied with this impedance xc of the car, which is a function of s because I'm working in Laplace domain. So then I have to subtract everything that is transmitted from xc to the xt. So in this case, I will have a damping term, c s times s, and I apologize, I selected s here from the suspension, and it makes a little bit of confusion with the Laplace operator s. And then I have to add the stiffness here, k s. So this is multiplied with the displacement of the tire. So this is x t of s. And this should be equal, because I don't have any other states connected to xc. Then this should be equal with sum of all the forces that are applied to the mass mc or at xc. So we see that for this case, we don't have any, and that's going to be easy, 0. So now we write the equation for the tire displacement. So that's the equation there. So again, in this case, we have I can start right here a little bit, so because we can focus on the mass xt first. So we have the inertia term there, mt times s squared. Then we have two dampers that are connected to xt, so I have to add those together. So that will be, I'm going to put here another parenthesis, cs plus ct. All of them are multiplied with the s operator from the derivative, and then I have stiffness ks and kt. So I have to put here ks plus kt. And everything in here, and it's better for me to use a bracket in here. So that would be, oops, that would be basically a bracket times x of t, because that's the displacement of the tire that I have here in Laplace. So that took care of all what's happening with the xt. But I have energy that's transmitted to this first state that should be subtracted. So I have here negative the damping term that I have cs times s. Then I have to subtract the stiffness. I mean, that's with a negative in front there. So that there times xc. And that's a function of s. So I took care of this situation here. That's the energy that was lost to this state. But I am also receiving some energy here. And again, it's energy received through this damper. So I have to subtract that here too. So I have minus CT plus, again, minus KT. This will be multiplied with XR. So let me just say here minus, and I'm going to put here parentheses, C of the tire, I think it's that there, if I'm right, yeah, times S plus KT, and everything is multiplied with the displacement of the road, which is also a function of S. And again, I have to add some of all the external forces that I apply to this mass mt that is displacing with xtd. So I don't have any external force, so that's going to be 0. So you can see that right away by observation, we can write the two differential equations very easy without drawing any free body diagram, because it will be a little bit complicated to end up with this. For you to using Newton's second law it will take you a little bit longer than we did it here. This same approach can be used for other nonlinear, other linear system, time variant system. So yeah, more complicated, and the more complicated the system it is, the more you see how this alternative of mechanical impedances is very, very useful in comparison with Newton's second law that will take it longer time to solve. Say, for this case, we have 3 displacement, and we have 1 external force acting there right on this mass M2. And we have, as you can see, 3 dampers and 2 springs. And we also have friction damping, and assuming that we have a viscous damping in here on the viscous friction there. So you can see that I can easily write, in this case, it's 3 degrees of freedom. I need to write 3 equations. So let's start with the equation for x1. So you can see that I need to put an inertia term there. I need to make a bracket here. So I have m1 s squared plus 2, this one is not connected to x1, so I will have only one damping term there, C1. Well, I do have another damping here, C1 plus C naught, both of them multiplied with S. Then plus I have 1 spring connected there, K1. And this should be multiplied with X1 of S. And then I have to subtract whatever is lost or received in this region from X2. So because that's the only connected, the way that it connects. So I have to subtract minus, I have C1 S plus, that's it. I don't have a spring connected there. So that's gonna be the only term, and I delete this. And this is multiplied with X2 of S, equal with all external forces applied here, which is none, so it will be 0. So we've done 1 equation already. Now we get to the second one for the second displacement, second state. So you can start, if you want, is from the left side, which means from x1. You can arrange them however you want in a nice way. I prefer this way. So I have to subtract whatever it's the contribution from x1. So that will be the damping term. So minus C1 times S times x1 of S. And then I have to add everything that's about this x2 state. So that will be an inertia term, m2 times s squared. Then I have a damping term here, another one here, and another one there, three damping terms. So that would be, say, C naught plus C1 plus C2. All of them are multiplied with S. Then I have one spring, one stiffness plus K2. And everything in here, it's multiplied with that displacement x2 of S. And then, as you can see, that x3 is also connected with the x3, so I have to subtract that term, so it will be minus, and it's only one spring that connects the two, so I have minus K2 times x3 of S. And it's going to be equal with all the forces that act at mass m2, which is this one. And we put it in Laplace domain, which is f of S. So that took care of the equation for the state x2. Now we can write the equation for the state x3. And again, we apply the same algorithm. And we see that this is connected with x2. So I will lose some energy there. It's connected with also with the ground, but the ground does, assuming that the ground doesn't displace it, so x displacement from the ground, it will be 0. So that term I don't have to subtract, it is 0. So let's start with subtracting x2. So I will have something like minus, I'll put here under the x2, so minus K2 times x2 of S. Then I have to add plus, as you can see, everything that's related to x3. So that would be some inertia m3 s squared plus some damping term here C naught and C3. And this will be multiplied with S plus some stiffness there, K2. And everything is multiplied with x3, pardon me, that's x3 of S. x3 of S, come on. And it's equal with 0 because we don't have any external force applied there. So as you can see, these are the three equations that form this, characterize this system, the equations of motion for this system. Three differential equations, which in this Laplace domain are algebraic, and they will be solved with, I don't suggest you to use it by hand to solve for the transfer function for these equations, or to do a free body block diagram to do it by hand if you want to. So we'll use for this case Python, and I'll do that in the next video when I show how easily can Python solve for this and give you the transfer functions that you need to characterize the system. Hey, this is George Bunjet with Engineering for All. I hope you liked the video. If you did like, please subscribe to support this channel and gives me more incentives to prepare next future videos. Thank you.